Alright, welcome. In this video, I'm going to go over some geometric principles, a little bit about the Pythagorean theorem and trigonometry, and why it's important to know these things when building or constructing things, right? So, main thing is that you understand that the right triangle is kind of the foundation of all the building principles, right? You could use it for plumb, perpendicular, and there's other scaling and other triangles too, but mostly everything we build is to, kind of off right triangles. And to construct that, basically here's your line. You want to get a perpendicular line so that it's bisected perfectly to 90-degree angles off of a straight line. So this is your baseline from a point. You want to get a perpendicular line. This is called the perpendicular bisector. But really what you're going to end up doing most of the time, well, that's possible if you want it to go both directions, and you're going to end up doing angle bisector. So this is just 180 degrees. Then you're going to bisect that from the line going out in one direction. Unless you need to, then you could do that. Generally, you're not going to have that kind of room. You might not have that kind of room, so you're gonna, let's say you don't have the option to work off of this side, then you're gonna end up doing something like this. You'll know from, you've heard the 3 4 5 triangle. Let's just draw one real quick. Point relative is 4, enter. Point relative is 3 vertical, enter, and then the diagonal there, and then you end up at the 3 4 5 triangle, and it's exactly 3 4 and 5 theoretically. Like that. All right, the reason why that's useful is in the field you can, here's your baseline. You're going to say the baseline's 4, and then the vertical line here, you get it by swinging an arc, because you don't know where this is yet, right? So you're going to swing an arc from here that's 3, right? And then you're going to swing an arc from this point that's 5, and where they intersect is going to give you your 3 4 5. Like that. And in theory it's exact, all right? You can use any multiple you want. 6 8 10. You could scale like these dimensions here. You could, or let's go back to this one, right? You could take tolerance multiplier 7, right? As long as you do that to this one, and then make it the same. So that'll be 7 also. And then here it'd be the same thing. You would have to upgrade tolerance multiplier 7, and it just, any variable right here, I just doubled it. 3 4 5 6 8 10. You've probably heard that one. And then these would just be like that. Computer's getting old and slow, man. Control R, and then this one will be the same. And it's useful because you may have, so if you want a 3 4 5, you can do it, but let's say you need to be 15 feet away. 3 4 5 is not going to help you much. 6 8 10 or 9 12 15, any variable of the 3 4 5 will work. There's also other Pythagorean triples. I think one that comes up a lot is 12, enter, 5, and 13. 5 12 13, that's another Pythagorean triple. It's exact. Alright. So the Pythagorean theorem is a squared plus b squared equals c squared. And then you can move that around with some geometry. I didn't really get into that here. But if you did 100 squared minus 6 squared, and it equals, and then you got the square root of that, you would end up with 8. Or 8 squared plus this squared would equal that squared, right? So the square root of 8 squared plus, let me just draw that real quick. To draw, so you're going to have So the way you would put it in the computer is kind of a little different than what you hear in school. So you go square root. And then put in parentheses 6 squared plus 8 squared. Sort of like this squared plus this squared is equal to the square root. So you just square root everything and you end up with this is equal to the diagonal 10. That would be your x. All right. So there's that, and then there's the any triple or any variation of the 3, 4, 5, or any variation, that'd be 10, 24, and 26, right? So let's look at this, right? So okay, so here's the square root of 2. So if you go to Tools, Calculator, it's sort of the same thing, square root of 2. So if you have equal sides, like in this case it's 1 and 1, it could be 5 and 5. That's a common one too, so we'll just do that. So square root of 2, parenthesis, and in this case it's times 1, which is just that times 1. It's just the square root of 2, 1.4142. That's a very common, it's kind of like pi. It's so then let's do that. So then I'm going to scale this one up. Control C. We'll go up here. Control V. And we're going to go scale it. Tab 5. Tab 5. Enter. Because that's a pretty common one too. So what I did on these, this is locked to scale. So I'm going to unfix that. What did I just do? Oh, I think I already had it. Control Z. Let's just do another one. Delete. So V. I'm going to go point relative 5. Tab. Enter. And then point relative tab 5. Enter. And then there. So what we're looking for is this. So you could go 5 squared plus 5 squared equals, and then get the square root of that. But you can also go, since it's a square root of 2 would be for 1, you just go square root of 2 times 5. All right, and that'll equal 7.0711. And that's a very good one to remember too, because the survey calls it a 55707. All right, so that's the square root of 2 is kind of useful, because if you don't have especially if you don't have a calculator that does square roots, that's kind of not as common, but sometimes it'll be the case. In fact, I guess you have to have the square root of 2, right? But if you can remember 1.4142, it's going to take you probably everywhere you need to go for building, because after that, your accuracy, you're going to start getting into instruments. You can't really. Once that scale 70711 or 707 1.4142 breaks down, you're into instruments, because you're not going to be pulling a tape for anything that's going to show up an error with that dimension, right, or that accuracy. So there you go. And then that was just explaining. You could go the square. If this was 5 and this is 5, then that would be the square root of 2 times 5. What I just did. All right, and so a lot of times you'll have something here, and then if you could use the 3, 4, 5, 6, 8, 10, and maybe this one be 15, so you go 16, 12, and 18, or 16, 3, 4, I'm not sure what the triple would be. You want the triple to be as the a squared plus b squared equals c squared, kind of like this, v. If it was that, it would be 18. I'll go this way. Point relative, if that was 4, it'd be 16. Tab, negative 16. Enter. What the hell did I just do? V. Point relative. Negative 16. Enter. enter 3, so that'd be 4, so 3, and then here would be 9, tab 9, enter. Yeah, it's not even close. So it would be better to flip it around, so it would be the other way, like this. Control H. Enter. It's just not a very good way to lay it out, right? It's not. You're going to lose accuracy because you're on the line and you're snapping the line and you're getting there. So the best way to do it is to actually calculate it. You know, this is 16.5 and this is 18. Let me zoom in. Let's zoom a little. So you'd use the Pythagorean theorem. So go Tools, Calculator. You're going to go square root of 16.5. You're going to use the caret sign before you hit squared, right? Plus 18 caret 2. Close. And then you're going to hit enter. 24.4182. So I'm going to copy that. So we know this one here is 16.5. So we're going to draw an arc. 16.5. It's going to swing through there, right? You got to make it a little longer when you start out because you're walking way over there and you really know where it's going to end up. And then you're going to go, and the same thing, you're going to create an arc from here. And it's going to be Control V. That's the 24.4182. And where those intersect is going to be right on the point that you want. So the nice thing about that is you're not getting any loss by snapping through the line through or snapping it way out here with a bigger triangle. And you're limited. You don't need more room. You don't a bigger triangle to get that point or a smaller one and then it's just much nicer to have it exactly where you want it. That's accuracy counts there. If you have an angle, so there's the right up here I told you a little bit about the sine, cosine, and tangent is the trigonometry, right? So you went a little bit Pythagorean theorem, so the close. This had it had geometry in there. Geometric principles, I guess. Principles. Right? Doesn't look right. Principles. Yeah, because it's spelled wrong, but you get the idea. Geometric principles. That's the things like this where you're bisecting a line. Circle theorems. I guess there's a lot of things like that that you could learn with the geometry class. Take a geometry workbook and go through it. In this case, here's our baseline. So to lay out this point, we know it's 16.5 feet away. Let me put that point in. I don't really know where that is yet along that line. So you know 60 degrees, and then you know this height, but you don't know this distance. You need to be able to swing two arcs here. So you could swing the 16.5, but you don't really know where to swing it from down below here. Okay, so I'm going to show you how I'll calculate that. So let's do a draw. Move my things around a little bit. So you're going to create a sketch of a triangle like this. You know this is 60 degrees, right? And then we don't really know this. Oh, yes, we do. Sorry, we do. We don't know that. We don't know that. We know this. And this is 16.5. So sine, cosine, and tangent. In this case, it's going to be the sine because it's the opposite side over the hypotenuse. So you end up with the formula that looks like this. The sine of 60 is equal to 16.5 over x. All right. So you're going to take the x going to go there. 16.5 divided by 60 will give you that length. So tools, calculator, 16.5 divided by sine of 60. And that'll give you Control C, Control V equals Control C again, and then Control V. So that'll give you that's the formula. So, and then so you already know this one, but you don't know this one. You're going to need to be able to have a point there. So you're going to go cosine of 16.5. It's going to be the same way because the x is in the same spot. This over this is the sine. This over this is the cosine. So it's going to be 16.5 divided by cosine 60. All right, you can copy that. Control C. Control. Something did something wrong. 16.5. 16.5 divided by cosine 60. Control C. That comes out 33 again. So let's do this. Cosine of 60 is equal to x over, we're looking for this one. We already know this one. So you could use, now that you have 33, you could have x over 33 would be the cosine, right? So, or you would end up with this over this is the tangent. Let's use that. That's kind of a common one. Or you could use, now that you know that this is 33, let's just do that. It was an even number, right? 33, I think. No, 19.052. This one here. So you could go tools, you could use a Pythagorean theorem. I'm going to go square root of 19.025 0526 squared this squared minus this squared 16.5 caret 2 close. Control C, compute, Control V. So you can calculate it that way, right? And then what you end up doing is this. So you're going to go along this line here, point relative, Control V. Not really. Just the formula. Okay. Nope. Control C. Point relative, Control V. And then that's your line 8 right there. Just an intersection. It's just a point on the line. You just measured over. Not going to swing an arc. You're just going to tape over. All right. And then you know that's 16.5. So now you can swing that arc. Didn't work. Oh, yes, it did. It just didn't end up on the page. 16.4 arc from there. And then this one was 19.05, right? So then you're going to swing that arc. We don't know where this line is really. It's in the drawings. All we know is it's from that point, and this is 60. We know the 16.5, we calculated where to put this so we could swing the arc. Excuse me. It has to be in exactly the right place, right? Arc has to be swung from this distance here. Has to be calculated. And then this one here, 19, so we're going to create an arc right there. This one is 19.0526. And then you're going to swing an arc right there. And then this line right here, F4, where those intersect, is going to be exactly where we want it. So there's no loss again, because you could use This, whatever this is, you could double that for the length, and you could do it with the 30 degree, 60 degree. So at 60 degrees, this is half of the diagonal, but most angles are not like that. So let's see, so V, let's see how close that is with that. It's going to be pretty darn close. Alt MA. And typically you're going to have some sort of error. There might not be much of an error here. Oh, there you go, 59.99999 or whatever you got. Because swinging the arc, this one's exact, but this one is not. If you took this down to more decimal places, it would be more accurate. This arc, and then the point of intersection would be a little bit more accurate. So depending on what that was, like if you took that and you went into I don't know how to take that up, and maybe I could do this. No, I don't know how to do that, but with the Excel you could calculate that more accurately. And if you were actually laying this out for a CAD drawing, you might want to do that. This program goes to 4 decimal places. I'm surprised it didn't get closer, because if you leave the formula, Control C, seems like arc would be more accurate, because it's not giving you the 4 decimal places. It's going right here, Control V, and then swing the arc. Nope. Delete. So 16 point, if we went like that, 16.5. 16.5 divided by cosine. No, the sine of 60. It should actually, Control C, should actually go better. No loss, right? So I'm gonna go right here, put that in with the formula, Control V, and then you'll end up with something that might be a little more accurate. Delete, zoom in, put this in, and then put it in the end right here. Get rid of that. F4. See if that came out closer to 60 degrees. Just out of curiosity how this program, Alt MA. Okay. So it's still same. It's the same. So internally it's going down to 4 decimal places. That's highly accurate. So if in the program, so let's just go through real quick something. So if you're on this point and you turn from here, turn horizontal angle left, turn 60, then it's exactly on that line. Then you shoot the distance, it would be more accurate. So let's say a lot of times I think you'll have an angle, let's say it's 50 degrees, and you have the length of this line, like at a parking stall or something, although that's an odd number, it'd be probably more likely to be something like that, is a 50. So what you end up doing is, let's say you're on an instrument and you backside and you turn 50 degrees left, and then you shoot your distance. That's how you do that. Otherwise you're going to lay it out the same way. So let's just do one more. So tools, calculate. I'm just going to do it the way I would do it without explaining it too much. Actually V, I would go V, J, A, away from this line. Going to go 50 from here, right? So it's going to give me along that line. And then go JD. So this, we know 50 degrees. And then 15, right? Okay, and then that would release me on that fixed point right there. I know that's not really helpful unless you're drawing. But, and then there's one more case right here. So this is pretty important, kind of the way getting from the basics to the most kind of like the thing that we use a lot. If you have a theodolite or a transit theodolite. Technically, I don't think a transit would help you much here because of the accuracy. You know, if it has vernier scales, that's probably going to be a little bit, well, depends on the accuracy you're looking for. They have vernier scales. Some of them are really accurate. Most of them that you'll get on a transit that you buy at Home Depot is not going to be accurate at all. I mean, they're going to be within an inch at 50 feet or 100 feet. But the theodolites, the digital theodolites and the old theodolites that have a microscope that go onto the glass dial are very accurate. So in this case, it's just a simple down and out, 22 feet along this line. And then what you would do is, I'll show you, there's two ways that you would do it, right? One is you measure along this line, there's your baseline, put a point there at 22 feet. And then you're going to go horizontally or perpendicular to that line 6 feet. So you would do a 3, 4, 5 or 6, 8, 10. So in this case, it'd be a 6, 8, 10 would be an even number. So you're going to go from there, tab, point relative, negative, 8, enter, and then swing your arc from that point. I think that's the right one, right? 6, 8, 10, right? And then you swing your arc at 10. And then this one swung at 8. Or swung at 6. And that would give you the crosshairs for that, right? And that would be exact. But usually what happens when you do this kind of thing, it's not exact. It's so in this program it is, but in the field, when you snap that line from A to B, this line's not going to be exactly where it belongs. You're not going to measure exactly where it is. So the theodolite will set you up, basically, so you set up on this point, you backsight this angle here, and set your instrument to horizontal angle right, and then you're going to calculate this angle. So the way you do that is Tools, Calculator, and then it's arctangent, A-tan of 6 divided by 22, and that's going to give you an angle 15.2551, right? And then to get the degrees, minutes, and seconds, because that's how most of your instruments are going to be, you have the degrees, so you delete the degrees here. You can multiply that times 60. That'll give you the minutes, so 15 minutes, right? And then you delete the minutes. And then you're going to multiply that again by 60. It's going to give you 18.3 seconds. So 18 seconds. I don't know. I should know because I've done the calculation out of curiosity, but 1 arc second's like a 1/16 of an inch at 500 feet. It's negligible. So if you're struggling to get your instrument to the 1 second, you're wasting your time unless you're shooting baselines or some control for something that's not building a building, but doing control for a neighborhood or something. All right, so hope that helps you understand a little bit of why geometry is important, right? The geometric principles, you get this out of a geometry, fundamentals of geometry workbook, all the stuff you would need to build for the rest of your life. Pythagorean theorem is really important because we use it a lot for calculating the distances so that we can swing the arcs. And then trigonometry, so you can just calculate stuff out there's no other way really other than, the only real way to do this is with trigonometry, and ratios would be good, so if you have you could understand similar triangles. And there you go, that's kind of it. I think basically we should probably call this fundamentals of building geometry, right? I hope that helps in your career and maybe get through school so that you can get more out of your career. And thanks for watching.